For 5.4, they're looking at linear transformations, and what they're saying here is that remember back when we did linear transformations and then we found a matrix for the linear transformation? That matrix that we found is technically a matrix that goes with a standard basis. So if you have a vector space and V that's in Rn, or n dimensional, it doesn't have to be Rn, and W, which is an m dimensional vector space, and T is a linear transformation from V to W, then we can associate a matrix that represents the transformation if we have a basis in V and a basis in W. And again, the bases that we've been doing are the standard basis vectors, the ij or ijk, basically ones in one slot and zeros everywhere else. And those are nice vectors to deal with. But what they're saying here is that you can come up with any set of bases and not necessarily the standard basis vectors. And if we define a basis vector for the domain and the range, or a codomain, or whatever they call it, then we can have a matrix that's representative or built from those matrices, or from those bases. So a vector in the domain is called x with a subscript of b, because that's the basis. And a vector in the range would be the vector with a subscript of c, because that's the basis. And so that matrix that you create is a matrix relative to matrix for t relative to the basis. And what they're saying here is that a diagonal matrix representation allows us to change the basis from the regular standard basis vectors to the basis vector that's formed by the eigenvectors. So if B is a set of vectors formed by the matrix P, which in this factorization is actually the eigenvectors, then D, the diagonal, is going to be your matrix transformation. And just think about how easy that would be to use a diagonal matrix for your transformation, because now you're only picking out the components. This theorem was proved in the book, and in the proof it didn't really mandate that D was a diagonal, so it turns out to be any similar matrix that would work for this. So here's an example, but let's see if we can dig one out from the homework. Let's see, I need to go to my homework. Homework. .4. I might as well change the due date now, huh? When's it going to be due? After the test. Friday? Sunday? Wait, what happened? So November 4th, it's due. Do we need to extend some of the other homework? So we have a test, so this has to be due before the test. I'll make it due on the 30th. So 5-1, 5-2, and 5-3. Chapter 6? We're not there yet. Yeah, so what I did is I unassigned it for right now, and then I'll throw it back up there. I know, and then it was past due, and then people were freaking out, so I decided to take it away. Understandably freaking out. So there were quizzes also. So there's chapter 3 and chapter 5 quiz. Chapter 5 is due tomorrow. Chapter 3 was supposed to be due. It's supposed to be due tonight. Uh, you want to do tomorrow? Sure. Oh, attempts. Number of attempts. Oh no, it's not infinite. Uh, it's 3. So somebody said that they tried it one time and then they couldn't do it anymore. So there should be 3 attempts. Where is it? Oh, there. This one already has 3 attempts. 4? Oh man. What has a website? Oh, math is fun. All right. Should we do 5, 6, 7? So why don't I do let's 5 or 6? 6. Let's do 6, and then I'll try to make another video for the rest, and then meanwhile I'll also try to upload the video so that you guys can see it. But I don't have to do it till after the midterm, huh? Cool. All right. Let's see if we can do number 6. Oh, I hope we can do this. It's hard. So this is problem number 6, right? All right, let's see if we can do this. We have a matrix matrix A. We have a set of bases B1 and B2. They're calling it B, and then they define T to be a transformation from R2 to R2, and since it's described by a matrix, it must be a linear transformation. So they want us to verify that B1 is an eigenvector for A, but A is not diagonalizable. Oh, so B1 is an eigenvector. So we can go through the process of finding the eigenvalues and then the eigenvectors and popping up. Hopefully one of them will turn out to be B1. But instead of doing that, let's just use the definition of what an eigenvalue means or eigenvector means. Eigenvector means that AX for this eigenvector X is equal to lambda X. And then whether we know lambda or not doesn't matter. So let's do this computation on this side. We have 3, 4, -4, and 5, and we want to multiply that by the eigenvector. We're showing that this is an eigenvector, -1, 1. And what we should come out here with is, well, we should come out with something that's a scalar of -1, 1, or a scaled version of -1, 1. And so let's figure out what this matrix multiplication is. So 3 times -1 is -3. 4, -3 plus 4 is +1. -4, -1 is +4. 4. Oh, this is a -5. This would be a +4, and then a -5, so that's -1. So it turns out that this is an eigenvector for the eigenvalue lambda is equal to -1. But it's supposedly it's not diagonalizable. So what does that mean? That means, I guess that means we have to look for the other eigenvector or other eigenvalue. So let's go through the process of finding the eigenvalues. Maybe we should have done this already. Well, we have one of them, but this is in R2, so we should come up with a second one. Ooh. So finding the eigenvalues, we take a look at the determinant of 3 minus lambda, 4, -4, 5 minus lambda. So that's 3 minus lambda minus 5 minus lambda minus -16. So what is this? This is -15, +5 -3, +5 -3, +2, and lambda squared plus 16. So that's lambda squared plus 2 lambda plus 1. So lambda is equal to 1, -1. Multiplicity 2. So we found one eigenvector already. Let's see if we can find another eigenvector. We can't. Because this is lambda minus, yeah, lambda plus, well, no, this is lambda plus 1 quantity squared. And so that has multiplicity 2. So we got one vector. We try to find another one. We're not going to be able to find another one. So let's try to find another one. So when lambda equals -1, our matrix that we want to find the null space for is 3 minus 1, or 3 minus -1, 4, -4, -5, minus -1. So this is 4, 4, -4, -4, which is going to give us, so we only have one free variable. We don't have two free variables. So then your basically your x here, your null set, your null space is going to be I guess -1, 1, x2. So that's the one eigenvector, only one eigenvector. So it doesn't match up. We don't have the same dimension as the two-dimensional space. So, so it didn't match up with the multiplicity. So conclusion here is not diagonalizable. Okay. So that's the first part. And then they want us to find the B matrix for T. Well, let's first, I guess we have the thing open. Let's see if we can answer it. Compute this. What do we get? One, -1. So express this as a product, and I think that was a -1 scalar that we got. And show that B is an eigenvector corresponding to the eigenvalue of -1. Should you put lambda? Lambda equals -1. Or maybe we should just put -1. And then the characteristic polynomial was, this is the one with the lambda. Lambda plus 1 squared, or lambda squared plus 2 lambda plus 1. Is that it? Oh, lambda is equal to -1. Boy, this is a lot of steps. Compute this matrix. We got this too. I mean, we went through the same thing, right? What was it? 4, 4, 4, -4, -4. Oh, number of parts remaining. This implies that the dimension of the eigenspace corresponding to the eigenvalue. So the eigenspace only had one vector, so it's a one-dimensional. This does not equal to the multiplicity of the eigenvalue. So that's basically what we concluded in our set of notes. So that part is good. And so they want us to find a B matrix for this. So let's find a B matrix for this. Well, we have a matrix. This matrix A is matrix A. What should we call it? It's a matrix for basis I and J. Or I guess they call it E1 and E2, right? The 1, 0 and 0, 1. So what we want to do is we want to figure out what the results are. So let me see if I can remember this. What we want to do is we want to look at the transformation as a transformation. So our matrix A was a 3, 4, -4, -5, right? 3, 4, -4, -5. So our transformation x1, y, x1, x2 is going to be a 3, x1, 3, 4, plus 4, x2, -4, x1, minus 5x2. That's our transformation. Right? So what we want to do is we want to figure out what happens to t of b1 and t of b2. Well, t of b1 is really a of b1, which we already figured out. What was that again? That was like 1, -1, right? So provided that our our basis for the space for the range space is still going to be standard basis. This is going to be one of your columns for your matrix. And then so we just need to figure out t of b2, which is a of b2, which is, what is it, 3, 4, -4, -5. And what was b2? 1, -2. So this is going to be 3 minus 8, 3 minus 8, -5, and -4 plus 10, -4 plus 10, +6. Yeah. So that means, so this is just another way to rewrite the transformation as a function of x and y, or x1 and x2. So x1 and x2. So that means, I don't know if we really, I don't think we really needed this, but I wasn't sure where we were going, so I figured out what that was. So that means if you were to put the b vector, which is -1, 1, that's b1. If you put that in here, you're going to get t of b1 is going to be whatever you get when you put 1, -1 into here, or -1, 1. So -1 in for x1 and +1 for x2 will give you a 1, and -1 for x1 and a +1 for x2 will give you a -1, which matches what we get if we applied the matrix. So that's one part. That's this t linear transformation part. The second part is that they say, according to the theorem, that your matrix with respect to the vector, the basis vector, is going to be the transformation evaluated at those vectors. So if b1 is a basis and b2 is a basis, then all I have to do is figure out what the vector is I get when I put it through the transformation. Now, whether I use the t that I found or I just use the matrix, it's the same thing. And then so my output here is 1, -1 for b1, and for b2 I get -5, 6. So the matrix that we're looking for, that's supposed to be the matrix for my new basis b, is going to be these things as my column vectors. So it's t of b1 and t of b2. And t of b2 is -5 and 6. So the subscript c would be if you were to have a basis for the range R and G. And in this case, the basis for the range is in R2. That's your range. And they didn't specify a basis for the range. So what we could do is we could just use the IJ or the E1, E2 vectors. So the standard basis. And if we're talking about the standard basis, then we're just assuming that it's just going to be whatever output it is, and we don't have to mess around with trying to change the linear combination. Some of the videos that I've already done talk a little bit about what happens when you have a different basis in the range, so you can take a look at that. But here, there's no C, so we have to assume that C is just a standard basis. And hopefully, this is the matrix that they're looking for. Yeah. This matrix contains a standard basis, so if I were to look at that, that's really this thing. Yeah, kind of. Yeah. So they draw a picture for this, and let's draw a picture after. Let's check the answer first. Make sure it's right. God, I hope it's right. It was that. So the B matrix is a 2 by 2 matrix with a 1, -5, -1, and 6. No. P is a matrix whose columns come from B, and with the B matrix transformation, that's what we did. What? What? Yeah, I know. Well, I kind of care. Oh, yeah. Oh, let's try that one. 1, -1. What were the eigenvector? -1, -1 was the eigenvector. So I think that was it. What? Oh, I'm guessing now. Yeah. The T of B is what? Uh-huh. You do. Why can't I do this one? Yeah, it looks like we need to find the inverse. Um, well, it looks like what they did was they used the B to be the P. The B1 and B2, they make the P matrix, and then so I have to find P inverse and then multiply it by A, and then find the P. Because that's one of the theorem. That's part of the theorem too that they say that the B matrix transformation comes from the bases form the columns of P. So the bases of B form the columns of P. And then here we actually have A, and then we want this new matrix C. And so what we have to do is we have to multiply by P inverse on the left and by P on the right. And that would give you P inverse A P. So let's do that. Actually, I'm going to go ahead and use MATLAB now, which you can use in your homework, right? No. I should maybe give you guys a MATLAB test. To the non-computer people. All right. So -1, 1. -1, 1. So B2 is 1, -2. So your B matrix, then your P matrix is this. The P inverse is still comes out with nice numbers. I mean, you can find the inverse of this real quick, right? 1 over the determinant, and then you switch the diagonals and negative the wings. And then A, what was A equal to? 3, 4, -4, -5. So if we multiply this P inverse of P times A times P itself, then this should be our B matrix that we're looking for. So -1, 4, 0, -1. What was it again? -1, 4, 0, -1. Oh, this is the final check now, huh? This is where everybody gets nervous. I ain't even tripping because I don't care if I get it wrong. um, yay! So yeah. So yeah. So I think the idea here, instead of considering these things, it turns out that so it turns out that A is actually equal to P times C, and C is a matrix that we're looking for. And then P is a matrix made of B1 and B2. So it's made up of those two vectors. Um, and so if we're trying to solve for A, or we're trying to solve for C, C is what we're trying to solve for, we would multiply this by P inverse on the left side, and then we'll multiply it by P on the right side. And then that's going to give us the P inverse here would cancel, and then there's a P inverse P that would cancel also. That would just leave us with C. So this is the multiplication that we want to get C. Well, that's the other part, is that we're not really diagonalizing here, because we found that this was actually not diagonalizable, and so we can still find and that's the other part of the theorem. It didn't say this in the theorem. It kind of said this after the theorem, that if so it didn't need to be diagonalizable, and so this can work for any similar matrix. So a similar matrix has to satisfy this equation. So if it satisfies this equation, then um, then as long as it's similar, it has this property, and it doesn't have to be diagonal. If C was a diagonal matrix, then that would actually be great for more computations in the future. But in this particular scenario, or in any other scenario, if it's not diagonalizable, if it's still similar, we still have this property. So this diagonal matrix representation is kind of a special case if it's diagonalizable. But if it's not, you can still change the basis this way. Oh, what was MB? That was this P. What we calculated here was what happens when we compute this B matrix. I don't see why this is wrong, but it's wrong, so I have to think about that. That's what I thought, but I don't think that's true, because it's wrong. Say it again. If you make a matrix with B1 and B2, well, no, well, that would be this. That would be the way to transform the matrix to a different basis. That's P. But MB, I thought MB was the answer, which is that C that we're looking for, but obviously it's not. So I need to figure out what happened. All right. Okay, we've sufficiently wasted enough time working on this stuff. Let's take a look at the review. I think so. Yeah, so now it's going to be a lot closer than it was last time. How close? I don't know, but it'll have 6 problems, I think. Uh, no. Well, I have a set of true false questions that you have to justify. So if you get it right but you don't justify it, then you're only going to get 1 point. But if you get it wrong and you're well, if you get it wrong but your justification kind of makes sense, you can still get partial credit for it if you got wrong. Yeah, so that would be partial credit. If the answer is true and you put true, but you didn't justify it, then I can't give you full credit for that either. So you have to say true and then give a justification. Yeah. Did you guys download the review already? Where was it? Okay, class lecture notes. There it goes. And just open it. LU. Well, I did, and then I gave you guys a quiz, and the quiz wasn't as good as I thought it was going to be. So I don't think it's on the test. Anyways, what? I know that should be the least of your worries. Um, so there's going to be a problem like number 3, where you have a big matrix, a rectangular matrix, and then the reduction is going to be done for you. So you just have to pull. So you just have to pull out the spaces, the row space, the column space, and then null space. So you guys should know how to do this. Well, let's see. The row is a subspace of a vector space, so this would be R something. Yeah, but if I ask for the dimension, you have to just give a number. So you have to read the question carefully. The dimension is based on how many basis vectors you have in each of them. It's not to throw you off. It's to. It's not. It's just different from this. That's all. Yeah. So I might ask for the dimension. I I don't. It comes from a good place. It's it hurts me more than it hurts you. Yes, and it's going to be painful to grade. Uh, we did talk about Kramer's rule, right? Yeah. All right. So, which of these do you guys want to do in sort of detail? Yeah, 3. I don't think we'll have time to do all of them. Yeah. Up. You might have to do that for B, but for A, I don't think you have to. Yeah. Sabrina? Number 6 also. So we'll do 3, we'll do 6, and we'll go back and do number 2. Is there 6? Oh, yeah. All right. Maybe we'll do number 3 first, and then number 2, and then we'll do number 6. Answer key. I thought about that, and I don't know if I want to just throw answer keys all over the place. Because I have to make it. No, I haven't. All right, review. Okay, so I think we can go through this kind of quickly um, because we have our reduced. This is all the way reduced. Yeah, this is a reduced row echelon form. There's a handful of things that we need to identify. Let's start with a column. The column, we have to look for the columns that have pivots. And so that's the first, the third, and the fourth column. And so what we have to do is we have to look at the original matrix, and we look at the first, the third, and the fourth column of the original matrix, and that's going to be your set of vectors. Those are your basis vectors. So that was easy. Uh, should I even write it? Yeah, so it's really just those three vectors, literally. So I would, it's separate three vectors because this is a basis. So we're looking for a set of vectors. So they need to not be a matrix. They need to be actual vectors. So that 1, 2, negative 3, 4, 0, 1, 1, negative 2, and 12, 0, 1, 5. Yeah, we skipped that one temporarily. Oh, we'll do it right now. So the row space would be the set of non-zero rows in your reduced row echelon form. Now, this one, you have the flexibility to, as long as you didn't do any row swaps, you have the flexibility to choose either the rows from the reduced row echelon form or the rows from the original matrix. So you can do one or the other. And if you do one or the other, just be consistent. So I can just say 1, 0, or 1, negative 2, 0, 0, minus 1, 0, 0, 1, 0, 3, and 0, 0, 0, 1, negative 2. You can write them as rows if you want also. I'll be flexible with the row. Yeah. Yeah. So I'll be flexible. You can write it either way. Remember, or you could just take the rows from the original set. So that's 1, negative 2, 0, 12, negative 25. And then I'll just put etc. here. For the column, it has to come from the original. To just use the original matrix, yeah. Right. So if you just, that's a good point. Pedro said if you don't want to confuse yourself, just get the information from the original matrix. All right, the null is going to be, this one's going to take a little bit more time, but since we have the original or the reduced row echelon form already, it's not going to be too bad. So let's got 1, negative 2, 0, 0, minus 1, 0, 0, 1, 0, 3, 0, 0, 0, 1, negative 2, 0, 0, 0, 0, 0. So for your null space, this is stuff that we've been doing already. In the, we have free variable in 1, 2, 3, 4, 5. X5. This has a pivot. This has a pivot. This one does not. So X2 is free. And then you just find the relationships between all of them. So from here, you get X4 minus 2x5 is equal to 0. So x4 is equal to 2x5. And the nice thing about the reduced row echelon form is that it's easy to solve for because there's a bunch of zeros and ones. So I'm just going to go ahead and solve for this one. X3 is equal to negative 3x5. And this one, x1 is going to be positive 2x2 minus or plus x5. So if you have a reduced row echelon form, then solving for, the x1s, x2s, x3s will be a lot easier because you don't have to substitute and replace because you already did that in the matrix. So our x is going to be 2x2 plus x5. X2 is free. X3 is minus 3x5. X4 is 2x5. And x5 is free. So things multiplied by an x2 and things multiplied by an x5. We have 2 here, 1, and nothing else. And then we have 1 here, 0, and minus 3, positive 2, and 1. Okay. No, so this one you can't just pull from the original matrix like the row and column spaces. Yeah. Yes. So whatever's free here is going to be your parameters for your solution. Yeah. I think you can. Yeah. Yeah. So the rank theorem says the column space. How many vectors do we have in our column space? 3. We're in a column space, and our null space has 2 equals 5. That's the rank theorem for this problem. Yeah, 3 plus 2 equals 5. If you put 5, that would be wrong. If you put 3 plus 2 without an equal sign, that would be wrong. 3 plus 5 equals 2. Well, that's what the rank theorem says. I mean, you can also say call space 3 plus 5 equals no.
You also told us 1 plus 1 equals 0, so I don't know. That could be true.
Rank plus nullity equals number of columns. Well, that would be column minus null equals rank. All right, subspaces. The row space is coming from R5. The column space is coming from R4. The null space is coming from R5. And again, I might ask you for the dimension of the column space, the dimension of the null space. But this is a way to actually, because the column space have 4 components, so they must live in R4. The row space have 5 components, and if you want to look at the null space also, that has 5 components. So it's a subspace of a bigger vector space, but in itself it's a subspace, so you also should be able to identify things like the dimension. Okay. All right, let's take a look at number 2. Maybe just 2A. So it says here to find the sequences of a sequence of elementary matrices so that this is going to be equal to the identity. And so what we want to do is basically do the row reduction and then keep track of what row operations we take. So one, 3, 2, 8. So the first one, multiply -2, row 1 plus R2, 1, 3. This becomes a 0. This becomes a -6 plus 8 is -2. No, +2. And then we want to reduce this. So row 2 times a half. And then we want to wipe out that 3. So row 2 multiplied by -3, add to row 1. And then that's it. So we have 3 steps, so we need 3 matrices. So we will denote that first matrix as E1. And let's perform this operation on the identity. So it'll be -2, -2, and then 1 in the bottom. So that's that. And then this one, our second elementary matrix is going to be 1, 0, 0, 1/2. And then our third elementary matrix is going to be 1 and then -3, 0, 1. So those are your elementary matrices. If I think we did this in MATLAB already, but you could do the multiplication here. So you could do a couple of things. If you multiply this in this order, and then you have A is equal to I, well, A, wait, E3, E2, E1 times A is equal to I, then that means the product of this must be A inverse because that's equal to I, right? So if you were to multiply this in this order, E3 times E2 times E1, then you would get the matrix. And you could do this by hand, I think, quick enough. Randall? You don't have to. I don't know if I can extend this anymore. The whole switching rows is usually not a good thing to do because that changes your determinant and stuff. It does some weird things. So we want to be careful about that. Yeah. Well, in this case, the instructions is find the sequence of elementary matrices such that this is true. So for that, I think this is my answer for this problem. I might follow this up with saying use the elementary matrices to find the inverse, and in which case you would do this multiplication, and then you would get the inverse. You could do that to check your work, but if I specifically asked you to find the elementary matrices first and then find the inverse using the elementary matrices, that's what I would like to see. But you know that formula for the inverse of a 2 by 2 matrix, so you might as well use it to check your answer. All right. All right. Whew. Now we only have 4 minutes to do that last one. Yay. So why don't I just show you the answers? Yeah. So A and B are invertible. Then A inverse, B inverse is the inverse of AB. That's false because why? You have to switch the order, B inverse, A inverse. Order matters for matrix multiplication. If the equation AX equals 0 has only the trivial solution, then A is row equivalent to the identity matrix. So this is true. That means A is actually invertible, and you do enough row operations, you can make it look like the identity matrix, which is one of our ways to find the inverse. For an M by N matrix, the solution of AX equals 0 form a subspace of Rn. The solution of this is actually the null space. That's what it's called, and null space is a subspace of Rn. Yeah. So in fact, problem number 3, we found the null space, and the null space is a subspace. So yeah, this is a subspace. But you should know that when you see this AX equals 0, then the solutions for that is actually the null space is what you're looking for. Yeah. No. No. Yes, you can have. It doesn't matter which one's larger. Um, if if the dimension they're different, but they could actually be the same too. So it could possibly be square. So there's when they say m by n, there's no restrictions on any of them. When they say n by n, they definitely, yeah, it's a square matrix. Yeah, it depends on which one's larger. Yeah. All right, this one, if the dimension of the null space of a 6 by 9 matrix is 4, so that's a null space, then the rank has to equal to 2. Is that true or false? What does the rank have to be equal to? It has to add up to the number of columns, and the number of columns is the second number in your dimension for your null space. So the rank theorem says that the rank of A plus the null of A, the dimension, the nullity, the rank of A plus the nullity is equal to the number of columns. So it has to equal to 9. 4 plus 2 does not equal to 9. All right, this one, the determinant of a triangular matrix is the sum of the entries of the main diagonal. What's product? It's the product. All right, as long as it's not 0. Well, if it is 0, then the determinant will be equal to 0, and then there's all kinds of other things that follow. That long list, right, that you should know. Good thing you guys have a sheet of notes, because you can write whatever you want there, really small. Um, a row replacement operation does not affect the determinant of a matrix. Oh, so when they say row replacement, that's the thing where you multiply a row by something and you add it to another row. That's row replacement. Okay, so that does not change the determinant. How about if you multiply a row by something? Does that change the determinant? Yes, it changes by that multiply whatever you multiply it by. How about if you switch two rows? Does that change the determinant? Yeah, by a negative sign. Okay, so this one does not change the determinant. If V1 and V2 are linearly independent eigenvectors, they correspond to distinct eigenvalues. Is that true or false? Because it says false. Why is it false? So you can have an eigenvector with multiplicity of 2 that could possibly generate the two linearly independent eigenvectors. Okay, so that's a possibility. So this is false. If A and B are n by n matrices, then the determinant of the product AB is equal to determinant A times determinant B. That's one of the first theorems that we learned in determinants. If F or if n by n matrix A is diagonalizable, or not if, an n by n matrix A is diagonalizable if and only if A has n eigenvalues counting multiplicity. Not necessarily. What would be a counterexample for this? Yeah, so I think it might have been backwards. Yeah, yeah. Yeah, so it could have n eigenvalues, but the diagonalizability does not depend on the number of eigenvalues. Right, that's true. That's true, and you can have that. Like in the example that we did in the homework, it has one eigenvalue, multiplicity 2. But the whole idea about being diagonalizable does not depend on the number of eigenvalues you have. It depends on the number of eigenvectors. If that's true, then that's the case, but that's not what it says here. What it says here is eigenvalues. It's counting only the eigenvalues, it's not counting the eigenvectors. Yeah, so if the eigenvalue has the same number of eigenvectors as the multiplicity, then it would be diagonalizable. Well, let's take a look at the example that we had here where we had this thing as multiplicity 2. So that's what that statement is saying. It's saying if this has multiplicity 2 and this is in R2, then it should be diagonalizable. But it's not because we found only one eigenvector. Yeah, you can have higher multiplicity. And then the last one is false because there's something that's wrong here. The definition. It's switched. So, okay. So this is it. If you want to look at the recording, you can see it, the answers. All right. Good luck on the test. I see you guys in Halloween. One sheet of notes. No, I mean, that's just what you're supposed to do.